Today we're going to be talking about how to sketch the area of the region bounded by the given curves. We're also going to, after we sketch it, decide how we'll integrate, whether it's with respect to x or with respect to y. We will also draw a typical approximating rectangle of the area and then label its height and width, and then we'll find the area enclosed by the region. So we've got 4 little steps here. The first one is to sketch the area of the region. We've been given 4 curves: y equals e to the x, y equals x squared minus 1, x equals -1, and x equals +1. So the first thing we need to do is sketch all 4 of those curves. That'll give us a picture of the region enclosed by the curves. So the first one that we can sketch is y equals x squared minus 1. That one's easy, and all of these should be pretty easy to sketch, but this will give us a good boundary of where other curves should go. So y equals x squared minus 1. Normally, if you have y equals x squared, it's just a parabola that opens upward with its vertex at the origin. In this case, we have x squared minus 1, and when you have a -1 attached to your x squared here, what that means is that we're going to move the vertex of the parabola down 1 along the y-axis. So our vertex is actually here. Now we can draw our parabola that opens upward. If we wanted to get x-intercepts, we could set y equal to 0. We'd have 0 equals x squared minus 1. We can factor x squared minus 1 to be x plus 1 times x minus 1, and we can see from that that our x-intercepts are -1 and +1, which we should know anyway because a standard x squared parabola, it's always 1 unit up, 1 unit over from the vertex. And then we also know that we have 2 units over, 4 units up, so we're going to have points here at 2, 3 and -2, 3. If our vertex were at the origin, we would have 2, 4 and -2, 4. So this is our parabola here, and we can go ahead and fill that in. Our next curve that we want to draw is going to be our y equals e to the x curve. And the important thing to know about y equals e to the x is that the y-intercept is here at 1. The y-intercept is at 1, and the curve looks something like this. It comes up like this and it intercepts the y-axis at 1. It never touches or crosses the x-axis, so it just skims along it here, and then it comes and curves up this way. So we have these 2 curves, and then we have the lines x equals -1 and x equals +1. So we'll have x equals -1, which will be the line here. So we'll have this curve, and then we'll have x equals +1, which will be the line here through x equals +1. And what we can see from this is that we have a region enclosed by these 4 curves that looks something like this. So this pink outline here is the region enclosed by these curves. So that's how you sketch it. Now, deciding how to integrate, whether with respect to x or with respect to y, is fairly easy. Basically, you need to look at your curves and figure out whether or not your curves look like they are roughly an upper and lower curve or a right and left curve. So what I mean by that is, in our case, we have this curve e to the x here, and we can label these e to the x and x squared minus 1. So this e to the x curve is, in terms of our region, above x squared minus 1, right? We have e to the x here, which is our upper curve, and x squared minus 1, which is our lower curve. This one is above this one, and so we really have pretty clearly an upper and a lower curve. If you had graphs like this, if you had a parabola that opened to the side like this, and maybe a line, x and y axis, something like this, right? And you're asked to find the area enclosed by the region. Well, you could kind of say that this parabola is the upper curve and this one is the lower curve, but it gets a little dicey down here, you know, at this level here, which one's upper and which one's lower. It doesn't make as much sense. What makes a lot more sense is that the line here for the area enclosed by the region in this area right here, The line is the curve to the right, and the parabola here is the curve to the left. So you have a rightmost curve and a leftmost curve, and the line is always to the right of the parabola for this particular area here. So in that case, we would want to flip it. In a case like this where we have a left curve and a right curve, we would want to integrate with respect to y. In our case where we have an upper curve and a lower curve, we want to integrate with respect to x. So we'll integrate with respect to x. We've made that decision. Now that we've made that decision, we can draw and label a typical approximating rectangle. So the rectangle that is going to approximate it, because we're integrating with respect to x, it's going to be a vertical rectangle like this. And usually what this looks like is just a rectangle. Oftentimes there's a dashed line down the middle of it, and this is just a rectangle that will approximate area. Basically what we're saying is if we add in a million little rectangles inside this region, vertical rectangles like this, we take the limit essentially as the number of rectangles goes to infinity, then we're going to be able to approximate this area. So we draw a vertical rectangle. In the case of a left and right curve, we draw a horizontal rectangle like this. So we draw a rectangle, and then when it's vertical, we want to label its height and width. Well, the width of it this way will be delta x, versus like this, the width of it would be delta y. And then the height of the rectangle, we can basically call y upper minus y lower, the upper and lower curve, versus here for the width of it or the height of it, we would call this x right minus x left, essentially. So we've labeled our height and width, and now we want to find the area. Well, the area in the case of our problem here, the area will be the integral from a to b. So in our case, a and b are -1 and +1 here, -1 and +1, because we have the left-hand side of our interval and the right-hand side of our interval. So we have from -1 to +1. And we want to say the upper curve minus the lower curve. So we say the integral of e to the x, our upper curve, minus the lower curve, x squared minus 1. And don't forget these parentheses. It's really important because we have a negative sign here. We need to make sure we distribute it across the entire lower function. So upper minus lower, and because we're integrating with respect to x, we do dx here. If we had right and left curves, we'd have basically these points of intersection here, which we call c and d, and we'd have the integral from c to d of the rightmost curve, so we'll call it x right, minus the leftmost curve, x left, and we'd integrate with respect to y. So that's how it changes. Now, in our case, finding area is pretty simple. We just simplify our integral and then evaluate. So we'll have e to the x, we're going to distribute the negative sign, so minus x squared minus a negative is a +1 dx. And now we can take the integral. So we'll get area equals, and when we integrate e to the x, the integral of e to the x is simply e to the x. When we get the integral of -x squared, we'll get -1/3 x cubed, and then +1 gives us a +x, and we'll be evaluating that on the interval -1 to +1. Now when we evaluate on the interval, we want to plug in the upper limit of our interval, then subtract whatever we get when we plug in the lower limit. So when we plug in the upper limit, we'll get e to the 1, which is just e, minus 1/3 times 1 cubed is just 1, plus 1, and then we'll subtract whatever we get when we plug in -1. So we'll get e to the -1. -1 cubed is a -1, so -1 times a -1/3 is a +1/3, and then we'll get -1. And now we can just simplify. So let's distribute our negative signs. We'll get e minus 1/3 plus 1. Then we'll get minus e to the -1, which is -1/e. We can move this e to the -1 to the denominator, and it becomes e to the +1. The sign on the exponent flips, so we get -1/e, minus 1/3 and minus a negative 1 is plus 1. Now, when we simplify, we'll get e minus 1 over e. So e minus 1 over e. That takes care of these two. Then we have 1 plus 1 is 2, minus 1/3, and then minus 1/3 is 2 minus 2/3, which is 1 1/3 or 4/3. So we get plus 4/3. And we could plug this into our calculator to get a decimal approximation, but it's cleaner to leave it this way so that we can see the exact area enclosed by the region. So that's it. This is the area of this pink region here that we drew, enclosed by the 4 curves that we were given in our original problem. So I hope you found that video helpful. If you did, like this video down below and subscribe to be notified of future videos.